Hello, Miss Walsh here, and today we're going to be looking at real world context. So applying what we learned about functions and their transformations to some real world problems. So let's take a look at this one. And we've got a cup that's filled with hot water and it's left to stand. The temperature T of the water after T minutes have elapsed is modeled by this equation. Okay, so first of all, don't panic. This is an exponential function and it's using the number e. We've mentioned it before, and basically e, known as Euler's number, is known as the natural exponential functions. So just pause the screencast right now, and if you can just enter the function in, because we are going to have to graph it, okay? The button E is found right here. So if you just go to Shift ln, it'll take you to that e to the x. Okay, so the first thing that it's asking us is asking us to determine the t-intercept. Okay, so let's label this. And what we have is we have lowercase being the time that's passed, the independent variable, and the uppercase is the temperature that we have. So when it's asking us for the t-intercept, what it's doing is it's asking us for the y-intercept. So we can substitute this in. E to the 0 is 1, so it's just a matter of adding these two, but we do want to be comfortable with technology. So a very easy way to find this is if you just go to this num, and I'm just going to set up my number back to the automatic like we had before, then I can right away see that the y-intercept is at 80.4. Okay, so we're going to label this. Be careful what the scale is going up by. It's going up by 5. So 80.4 will be just about here. State a contextual interpretation of the t-intercept. So what does this mean? What is this 80.4? Well, it's temperature, and it's when the time was 0. So what's happening here is this is the initial temperature. So if this is a cup of tea, then this is the temperature of the water that was poured into the cup right at the beginning. State whether the function displays growth or decay. Okay, so let's just hit plot on this. As you can see, I have a nice graph here. You're going to have to be clever with setting up the window. You can try auto scale, but basically the number of minutes are going by. So we can go to Shift Setup. And in order to get this nice graph, plot setup, I started at 0, and then I can already see that it's going to want me to plot it over a lot of time, so I made it up to 125. We know the y-intercept is 80.4, so you can make this 0 to 100, something like that, but you can see from the numbers that you're going to need a pretty high y-axis. So when you have your nice plot, then you can see that this is decay. So decrease, the opposite of growth. And how the growth or decay relates to the cooling of the water, well, what's happening here is that as the water cools, the temperature is decreasing. So it's the temperature that's decaying, okay? So now for the next one, we need to determine the horizontal asymptote of the function. Okay, you can think about your transformations. This is some sort of a stretch, and this right here is what we went up by, and so you can ration it out, or remember the other way for you to see your horizontal asymptote is just to see what is the function tending towards as the x's go really, really large. So let's go to that Shift num, and let's go to starting at like maybe 1,000. And then when you go back to that table, you can see what's happening. Oh, okay. So basically we're getting really, really, really super close to 24.5. And it's because remember the exponential functions have an asymptote of 0, but you have that vertical shift there, okay? So our horizontal asymptote is going to be, and we're going to write it as equation, as 24.5. And I'm just going to draw it right away. And somewhere 24.1, so this is 20, this is 25, so it's going to be somewhere there. And then you go ahead and draw this dashed line. So state how the horizontal asymptote relates to the physics of the cooling of the water. What does this mean? Well, basically, after a while, and I'm just going to draw this graph since we're already so close, this at some point is going to get incrementally close to this 24.5, and it's not going to get any colder. So we can say that basically the 24.5 is the room temperature. And once it's cooled as much as it could, then it's not going to cool anymore. That's sort of the real life context of that asymptote, yeah? So if you left your tea at that room temperature and came back to it tomorrow, many minutes later, then it would still be at that room temperature, right? It's not going to get to freezing or something like this. Okay, so determine the range of the function in the given domain. Okay, what's our range? Well, we know that our smallest temperature is 24.5, that it's technically never quite reaching. And then we know that the hottest that it was 80.4. That was that initial one. Notice that it's talking about within the given domain, and that's because the domain here is just the t greater than 0. Okay, you don't have negative time, so even though we could draw this tail little here, technically it's just this part of the function, okay? All right, we've already sketched the graph because we're so awesome. And so the last part is just determine where the water will be 40 degrees. We've seen problems like this before. So it's saying, take this function of the cooling and solve this. Now to solve this algebraically, we would need logarithms. We're not interested in logarithms right now. And so what we're going to do is we're going to do this the graphical way. y1, y2, and then of course, as soon as you solve it with your calculator, you do want to just indicate that on as well. So I'm just going to draw this 40-degree line and indicate that in fact, what I'm looking for is this. So let's go to our calculators, and perhaps you already did, and I'm just going to go to the plot and let's enter that 40 in here. And then when we plot it, there it is. And then, just go to intersect. And what we have is 47.7 about minutes. Which makes sense, right? If you left your tea standing there for an hour and it's relatively warm, perhaps your tea may still be warm, but it's certainly not going to be anywhere near where you started. Okay, so that's applications. The one that you will have to do in the do now is, give it a try. Bye.